Hello, in this video we will see the exponential signal given as e to the power st. Okay, where s is in complex in general given by s equal to sigma plus j omega. Therefore, we can write e to the power st as equal to e to the power sigma plus j omega into t, which is equal to the power sigma t into to the power j omega t. Now, from Euler's identity, we can write e to the power j omega t equal to cos omega t plus j sin omega t. Therefore, this is equal to e to the power sigma t into cos omega t plus j sin omega t. Now, since S is complex, so its conjugate will be sigma minus j omega. Therefore, e to the power S conjugate t will be e to the power sigma minus j omega t, which is e to the power sigma t into cos omega t minus j sin omega t. Okay, let us call this equation 1 and this equation 2. So from equation 1 and 2 we can see that to the power st plus to the power s conjugate t will be equal to cos omega t plus j sin omega t plus multiplied with e to the power sigma t, and here cos omega t minus j sin omega t. So upon adding this term will be, this sin term will get cancelled and we are left with twice e to the power sigma t into cos omega t. Therefore, we can say that e to the power sigma t cos omega t is equal to e to the power st plus e to the power s conjugate t divided by 2. Let us call this equation number 3. Now we can see that the function e to the power st is the generalization of the function e to the power j omega t, where so in this generalization the frequency variable j omega is generalized to the complex variable s equal to sigma plus j omega. Therefore, this variable s is called the complex frequency. So s is called the complex frequency. Okay. Now we can see that this function e to the power st is a generalized signal. Okay, and depending on the value of s, this gives various different signals. For example, in first case, when s is equal to 0, then we can get some k equal to k to the power 0t. So this is a constant. Okay, in this case s is equal to 0. So when we put s equal to 0, we will get a constant signal, which is this k. Okay, and if we plot it, we'll get the signal of constant amplitude k. This is time t. This is e to the power st, where s is equal to 0. Now in the second case, the signal e to the power st will be a monotonic exponential, which is e to the power sigma t. And this will be in the case when omega equal to 0 and s equal to sigma. Okay, and so its graph will be like this when sigma is less than 0, and it will be an increasing exponential when sigma is greater than 0. Okay, now in the third case, e to the power st will be a sinusoid, and this will be when sigma is equal to 0 and s is equal to plus minus j omega. Okay, so we'll get a sinusoid cos omega t, and its graph will be okay. In the fourth case, this will be an exponentially varying signal, exponentially varying sinusoid, and this will happen when s is equal to sigma plus j omega. So we'll get a sinusoid of this decaying magnitude. So this is when sigma is less than 0, and it will be an increasing sinusoid when sigma is greater than 0. Okay, so in this video we have seen that the general complex exponential signal e to the power st gives four types of signals: a constant when s is 0, and it gives us a sinusoid when s is equal to plus minus j omega. In this case, sigma is 0. And third, it gives a real exponential signal e to the power sigma t, and in this case s is equal to sigma, and in the last case it gives us a exponentially varying sinusoid, and in this case when s is sigma plus j omega, and depending on the value of sigma, whether it is negative or positive, its amplitude will be growing or decaying. Okay, and I would like to mention here that here omega is known as the radian frequency, and it gives the oscillations, and the sigma is known as the Napier frequency, and this is responsible for the growing or decaying magnitude. So we'll stop here. Thank you.